Superposition Lecture 3. Let's do a recap on what we have done for standing waves. First, we have looked at standing wave in two fixed ends, or we call it the closed end in the string. So at the fixed end line, we have a node. Similarly, the other fixed end also. From there, we can work out the wavelength of the standing wave in terms of the length of the string. As you can see here, the waveform is half lambda, so the length will be half lambda. So from there we can work out the wavelength to be 2L, where L is the length of the string, and using V over F lambda will be work out the. And for n harmonics, we can actually generalize the formula to NV over 2. Similarly, we have looked at one. We usually call this the closed part, and this is the allow frequencies and harmonics. And open to allow frequency to be also Fn equals to Mv over 2. Also the two open ends and the two fixed ends. There is a one fixed end and one. And all the discussion above, right? All this formula here for the allow frequency, okay, all these observations apply to both transverse as well as longitudinal waves. Let's take a look at example 3. We are asked to calculate the length of a closed organ pipe. When the question says closed organ pipe, this is a one end open and one end closed pipe. And part B, an open organ pipe. Open organ pipe will be 2. We are told that the fundamental frequency that each end produces 256, and the speed of sound in air is 3. To solve for this kind of questions, whether it is standing waves that are in string or any other medium, there is no need for us to memorize the formula that I showed you just now. It's only for you to memorize this one. All you need to do is draw the box with the correct type. So for part A, our closed organ pipe, it will be 1 and open 1 and closed. So I know that the wavelength is equal to velocity over frequency. Velocity is given as 330, frequency is 256. This is the fundamental node, so the waveform will look like this. At the closed end, it must be a node. At the open end, it must be an antinode. The longest wavelength or the lowest frequency that you can have is when there is exactly one antinode, one node. So this gives you lambda. We mentioned about end correction, which is the E here. The antinode is not formed exactly an open tube, it is slightly outside the tube. So we need to pass the distance E. So L plus E will be 0.25 lambda. But in this question, there's no information on end correction. So the length of the pipe is 322. So we are assuming that the end correction here is negative. For the open organ pipe, the open ends have to be standing wave is formed. So the lowest frequency, which is also the longest wavelength that you can get, is when half lambda inside the tube. So again, from here we know that half lambda will be equal to L plus E. So that is about 0.645. And in both the calculations, we are assuming that the equation is equal. So the length of the tube is just example 4. Here you have a tuning fork. The tuning fork is made to vibrate above tube water. So the vibration of the tuning fork will form a standing wave air quality. We we are told that the water is allowed to run out of the tube. A loud sound is heard when the length of the air column is L1 and again when the length is L2. A loud sound means a standing wave is formed, that is resonance. So the first loud sound is heard when the air column has a length of L1, so that will be the fundamental frequency. The next one will be when the length is L2, so that will be next higher frequency. We also calculate the wavelength of the sound in the tube. So again, we just need to draw the waveform. At the water end here, right, this will form a node because the air particles will not be able to vibrate into it. This is how the waveform. When the water level is at L1, the length of the air column is L1. That means this is the lowest possible frequency. Open end again have to be an antinode. Closed end have to be a node. So the lowest frequency that I can have is when it's exactly. So L1 plus end correction will be a quarter. Then after that, I have the next loud sound when the air column is L2. So the waveform here will be exactly 3/4 lambda. Again, satisfy the condition that the open end must be an antinode, the closed end must be a node. And the next lowest frequency that I can have is such that this is exactly 3/4. So L2 plus E is 0.75. So from here, I can take equation 2 minus 1, and therefore the wavelength is just 2 times of L2 minus. Here I actually can eliminate end corrections because I'm using the same tube. So I don't have to make the assumption that the end correction is not. Unlike just now example, the previous example, because we're using different tubes, so we do not know end correction. So in that situation, we have no choice but to assume correction is not. But here there is no need for such assumption. So whenever possible, you need to take into consideration your end correction. And then now we are done with standing waves. We move on to the next section, which is about diffraction. As you can see in the animation here, diffraction is the spreading of the when it's passing through an opening, which we call an aperture, or when it's passing through an obstacle, like this. Then you can see that the waves start to spread or to bend around the obstacle. The first diagram that you see here, this is the water waves passing through the breakers. So in between the breaker is formed a natural aperture, so you can see that the waves start to spread. So the definition for diffraction is it is the spreading or the bending of the plane waves when they encounter an aperture. Aperture is an opening like this, or obstacle, this one, whose linear dimension is comparable to the wavelength of the waves. Linear dimension will be referring to the aperture, the width of the aperture. For the obstacle, it will be the thickness of the width of the aperture. There will only be significant spreading or diffraction when the width of the aperture is comparable to the wavelength. Okay, these are wavefronts that are coming in. A distance between two wavefronts will give you the wavelength. So the wavelength have to be comparable. Generally, there will be more spreading if the wavelength is longer. And one thing very important you need to take note is that during spreading, the wavelength remains the same. So the lambda, that is the distance between the wavefront before the spreading, and the lambda distance after the spreading must stay constant. Okay, this is the example that you see for water waves. Actually, not only water waves spread, the other type of wave also. For example, sound wave. Okay, imagine this is the lecturer talking, and the door in the lecture hall is open. I have a student standing behind the wall. This student will be able to hear the teacher's voice. Because why? The wavelength of sound is comparable to the width of the door. Here. Since we know that the width of the door usually is about a meter approximately, and to calculate the wavelength of the light, I need the velocity of the to calculate the wavelength of the sound, we need the velocity of the sound, which is about 330. For convenience, let's take the frequency of sound, 330 hertz or thereabout. You'll find that the wavelength is approximately a meter. So it is comparable to the width of the aperture. As a result, you see spread. So a boy standing behind the door will be able to hear the sound of the teacher. However, he is not able to see the teacher, okay, because it's blocked by the wall, and also because the wavelength of the light of the order of 10 to the power minus 7 meter is too small to spread around the door. So you don't see the light spread much. And that's the reason also why the boy cannot see the teacher. Light wave also spread. In this case here, we have a laser beam pass through a slit. A slit is like an aperture, so it's an opening. So when this happens, it will start to spread. And if you have a screen on the other side to capture the image, you will be able to see something. Without the slits, right, you will just see one bright spot on the screen. But with the slits, okay, this is what you will see when you pass the light through the slit. If it's one slit, that means one aperture, you will see one spread of, I won't call this a spot, okay, a spread of brightness somewhere in the straight through position, and then there is a dark region, okay, follow on the other side. So this is about the same. And then if you're lucky, you might be able to see the next brightness. So this is the case for one slit. There is one aperture. In the case where you have two slits, you start to see many spots. Okay, right in the straight through position, you will see a bright spot, then there is a dark region over on this side. These two sides is the white spot. Followed by that, you have the next white spot. We call this the first order white spot. The one in the middle, we call it silver region. And then we have dark again, here also, followed by the second order bright spot. Dark. Then you have the third order here. When the number of slits increases, 3, 4, 5, 7, you can see that the spots, right, are becoming clearer and clearer to see. And also the intensity of the spots will be higher. So now we are going to explain the spots that we see on the screen. For your syllabus, we need to know single slit. There is one slit pattern on the screen. We need to know two slits, the pattern on the screen. We also need to know grating, which consists of thousands of slits, okay, and how the pattern look like on the screen. So I will start with two slits, or we also call it two source interference. I'm going to define for you the definition for interference. The interference refers to the phenomena of two or more waves must be of the same type meeting at a point in space. So they must meet at the same point, otherwise it won't be any interference. And they must be of the same type. Water wave and water wave, they meet, and then it will produce a resultant wave. So it produces a resultant wave pattern, and this pattern like is given by the principle of superposition when they superpose. There are three conditions that need to be satisfied in order for you to see the pattern that you saw just now on the screen. So here we are looking at the conditions for two source interference. The conditions here apply for two slits. Two waves must be coherent. So if we have two slits or two source, then the waves that meet and interfere on the screen must be coherent. Coherent means they have a constant phase difference. Remember, we use angle to describe phase. So when we say they have constant phase difference, that means the angle, the difference in the angle between the two waves must be constant. So you imagine that the two waves are points on the circle. So that means the relative positions of these 2 points must be fixed. Let's say if they are at an angle of 90 degrees apart, then you must maintain that constant 90 degrees apart, same phase difference. Or they can be in phase, that is they are exactly the same point on the circle, then phase difference is 0. Okay, they can be opposite of the circle, that means a phase difference of 180. So it doesn't matter what is the phase difference, as long as they have constant phase difference, you'll be able to get the steady interference pattern. So that is coherent. The second condition is only for transverse wave. So if you have two waves that overlap, and to get the pattern that you see on the screen, they must be polarized or unpolarized. When you say they polarized, they must be in the same plane, because principle of superposition is the vectorial addition of the waves. So if they are not polarized in the same plane, they cannot cancel completely, and therefore you don't have a dark region. Okay, so you must make sure that the two transverse waves are in the same plane in order to see the bright dark patterns. And the third condition is the two waves must have roughly the same amplitude. Again, if the two waves do not have the same amplitude, then it is not possible to have the dark region, because in order to have the dark region, we need to have destructive interference. So the two waves must cancel out. In order for them to cancel out, the amplitude must be roughly the same. Okay, so now we're going to look at a point P, which is on the screen. Let's suppose that these are my two sources, S1, S2. So the light from S1 will travel and hit on the screen at point P. Similarly, the light from S2 will travel along this path and hit the point P. So now my question is, will it be a constructive interference or a destructive interference at the point P? Meaning, will it be a bright spot or a dark region at the point P? Remember, for constructive interference, the waves, that is these two waves from S1 and S2, okay, they must reinforce each other such that the amplitude is the maximum. So you see that at this instant, right, the two waves have zero displacement P, so the resulting displacement is 0. But the next instant, the displacement will add together, and you will have at a quarter T later, you see that 12 and the 12 T will be at the point whereby the amplitude, right, is actually double that of the individual wave. And when the amplitude is double, intensity is proportional to amplitude squared. You find that the intensity will be 4 times more. So it is a very bright region. Okay, although at this instant, right, when it's zero displacement from S1 and zero displacement for the wave from S2, the resultant amplitude is 0, resultant intensity is 0, but because the wave is coming so fast, right? So you can imagine this point, actually the intensity fluctuates from 0, then to a maximum, and then to 0 to a maximum, but the fluctuation is too fast for you to observe. So what you see at the point P is just a bright spot, but by right it's fluctuating very fast. So that is constructive interference. I'm going to discuss with you the condition for constructive interference. So the definition for constructive interference is it will occur at points where the waves meet in phase. They meet in phase, that means they have the same phase, same angle on the circle. Then they will reinforce each other. That means the resultant displacement will be larger than the individual. We can check by looking at the path difference, whether it's a constructive or destructive, whether they meet in phase or not. So what you can do is, as the name implies, path difference means the difference in the path. We have to find the distance from S1 to P, and we can calculate that in terms of wavelength. So let's count S1 to P first. This is 1 lambda, 2 lambda. How about S2 to P? This is 1 lambda, 2 lambda, 3 lambda. The path difference is exactly 1 lambda. So when it's exactly a path difference of 1 lambda, they will always meet in phase. So a general formula will be when the path difference is equal to n lambda, where n can be 0, 1, 2, or 3. So whenever the path difference is exactly an integer number of wavelengths, it will be constructive interference. Now we're going to take a look at another point P, which is also on the screen. Will this point P be a dark or a bright region? So same thing, we are going to look at how the wave meet. So at this instant, both the waves from S1 and S2, they are having zero displacement, so the resultant amplitude is 0. And then the next instant, you can see that well, the one from S2 have a positive displacement, but the wave from S1 have a negative displacement, and they are identical, right? So the resultant at any time will always be 0. Even when it's a quarter period later, one is having positive amplitude, the one is having negative amplitude, so the resultant will be 0. So the resultant displacement at the point Q is always 0, and therefore the intensity is always 0. So Q is a dark region. So what is the condition for destructive interference? Destructive interference occurs at point like Q where the waves intersect exactly out of phase. When they are out of phase, they cancel each other. So they must be, if you imagine a circle, if one is at the top of the circle, the other one will be at the bottom of the circle. If one is on the left, then the other one is on the right. So they're exactly out of phase. That means the phase difference is 180 degrees or pi radian. Same thing, we can look at the path difference. So if I were to calculate the distance from S2 to Q, 1 lambda, 2 lambda, 2.5. How about S1 to Q? 1 lambda, 2 lambda. So the path difference is half lambda. So the general formula for destructive interference is it must be half of lambda in order for it to get destructive interference. So it can be n plus half lambda. So where your n can be 0, 1, 2, and 3. So when it's half lambda, 1.5 lambda, 2.5 lambda, 3.5 lambda, they will all be destructive interference. Okay, if you refer to your lecture notes on page 16, there is a footnote saying that the above equation, okay, the path difference that we just discussed, will only be true when the two sources are in phase, meaning your S1, S2, right, they produce identical wave. Produce a crest S2, S1 also produce a crest. If your S1 and S2, they're exactly out of phase, meaning when S1 produces a crest, your S2 produces a trough, so the phase difference is 180 degrees, then the condition for destructive interference will now be the condition for constructive interference. So the condition is changed. So you need to be very careful. You need to check whether S1 and S2 they are in phase or they are out of phase. We don't do any other phase difference for the two sources. Okay, so only these two, in phase or out of phase. Then there's another set of formula beside the path difference. You can also work it out in terms of phase difference if the question given is such that it's in phase. So we learned from the wave lecture, formula for phase difference is path difference over lambda times 2 pi. So for constructive interference, if you sub in path difference to be n lambda, and then you cancel the lambda on top and below, you end up with 2n pi for constructive interference. So whenever the phase difference is 2n pi, 2 pi, 4 pi, 0, this will all give you constructive if the two sources are in phase. Then for disruptive interference, same thing, we have path difference to be n plus half lambda. So if I sub that into this equation and I simplify, I'll get 2n plus 1 pi for disruptive interference. So when it's pi, 3 pi, odd number of pi, it will be disruptive interference. Because when this happens, the two waves will always meet out of phase if the two sources are if the two sources are in phase. That means they produce identical waves. Similarly, the equation right for phase difference will exchange if the two sources are out of phase by 180 degrees. So if they are out of phase by 180 degrees, 2n pi will then be the condition for disruptive interference. 2n plus 1 pi will then be the condition for constructive interference. So now we move on to experiments on two-source interference. Some of the experiments that I've given you in the lecture notes include the Ripple tank and the Young double slit experiment, which is about the light. Here I'm going to talk about the sound, but the discussion that I have here, right, goes for the water waves as well as the sound wave, okay, because they are all waves. Okay, I did this lecture demo in the lecture. So if you recall, I have an online signal generator. And it is connected via my laptop to the loudspeaker. So when I switch on the tone generator, sound wave will be produced. So these are the waveforms. Okay, the continuous line that you see here represents the crest. Then the one in the middle, okay, that is the trough. So the wave from L1, loudspeaker 1, spread out this way. Similarly, the wave from speaker 2, L2, spread out this way, and we can see that there is some interference here. So supposedly at the point P, if you're seated at the position P, would it be a constructive or a destructive interference? As discussed in the lecture, we can look at the path difference. So if I were to count the distance from the loudspeaker L1 to P, this is approximately 1 lambda, 2 lambda. So by the time the wave from L1 reaches the point P, it will be the crest. Similarly, from loudspeaker L2, the distance is approximately 1 lambda, 2 lambda, 3 lambda, 4 lambda. So it's also a crest. So the path difference between these two waves will be exactly 2 lambda. So at point P, we have constructive. Instead of looking at the path difference, because you have the wavefront, you can see the crest and the crest meet, so you can tell straight away that it is constructive interference. So let's take a look at another point Q. Would it be constructive or destructive interference? Again, if I look at the path difference, okay, from L1, this will be 1 lambda, 2 lambda, 2.5. That's why it's a trough. But similarly for L2, it is also 1 lambda, 2 lambda, 2.5 lambda, another trough. So the path difference is 0. So at Q, we actually have a constructive interference. And the path difference is 0. Although it is the trough and the trough, but they still superimpose to give me an amplitude of minus 2a. Intensity is proportional to amplitude squared, so the intensity is still the maximum there. Another point R, so same thing, you can work out the path difference. It is 1.5 lambda, or you can look at the wavefront. One is a crest, the other is a trough. So when you superimpose these two, you add these two together, they cancel out, and therefore it will be a destructive interference. Okay, so this is similar to the circular wavefronts that are given to you on page 17. Okay, there's a checkpoint on page 17. If you refer to the diagram given there, this is similar to what we have discussed. This here refers to the water wave. So these two, instead of loudspeaker, okay, the two sources here are the two dippers that dip into the water. So they produce circular wavefront like this that you see that overlap in space. At this point here, they are all constructive interference. And along this line, the path difference is 0. Okay, similarly, if you find this line here, this dotted line, along this point, we have the crest and the path meter, so it will always be destructive interference. And you find the path difference, they are all having the same path difference, which is half lambda. And then next you have another constructive interference, where the path difference here along all this point, along all this line, all points along this line have a path difference of lambda. Similarly, if we go the other side, it is the same thing. So you have path difference of half lambda and then a path difference of lambda. So according to the questions, lines such as C naught, okay, I call this one in the C naught because path difference is 0, C1 because path difference is 1 lambda, and this is C1 prime, and because it's on the other side, this is also path difference of 1 lambda. They are called anti-donor because these are all the maximum amplitude. But these are not stationary. You just use the term. And then the D is where you have the destructive interference, where the displacement is always 0, so we call it a nodal line. So can you identify other antinodal and nodal lines in the interference below? Okay, on the screen, on my screen is below. On your note is above. Okay, so this will be your answer. There are another one here which have a path difference of 1.5 lambda. So this will be destructive interference, nodal line. Then there is a path difference of 1 lambda. So this is donor line. So this will be a constructive interference, C. Another one here which have a destructive interference, path difference of half lambda. This one is the same as this one here. And so I can join them together like this. So it will be straight, then the middle curve slightly, and then curve out. Similarly, right in the middle here you have constructive interference. I didn't join them together, but you can. Then you can join them together, it's a straight line. Along this line, this is the same line, the path difference will be all 0. Similarly, this line here, the path difference is all 1.5 lambda, so it's destructive. And then we have C1, okay, you can join the line also, this will be all constructive interference. Okay, so for the little tank, what you see would be like this. Along the region where you have the donor line, you see there isn't any waveform because there is cancellation. Then along this region where there is constructive interference, antinodal line, you see that the waves become very clear, okay, because the amplitude is above. So they reinforce each other. This is constructive interference. You have another one here. This is your C1. And then you have another one here. This is your C2. Another one here. This is your C3. And probably another one here. Which is C4. And the destructive interference is a V1, V2, V3, V4. And the same thing repeats on the other side. Okay, we are done with the sound wave and the water wave with the tank. Then now I'm going to talk about a very famous experiment involving light, which is called Young's experiment, Young double-slit experiment. Okay, Thomas Young, the scientist behind this experiment, he actually conducted this experiment to find out the wavelength of the light that he is using. Because about 200 years ago, technology is not so advanced, they are not able to measure the wavelength of the light since it is very small, in the range of 400 to 700 nanometer. So Thomas Young actually conducted this experiment using a double slit, measure the distance of the bright spot on the screen. He was able to find out what is the wavelength of the light source that he is using. Now let me explain to you the setup. It is quite similar, okay, to any other waveform, whether it's sound wave or the water waves. But for this light wave, we have a double slit here because we have to get coherent identical light sources, and the only way to do it right is to use one light source and split it into two, so that the waves that emerge out will be coherent. Then you have a screen on the other side. You will see the bright and the dark fringes. Okay, so this graph here is the intensity graph. When the spot is very bright, the intensity is very high. Okay, then you go to a region where you have destructive interference, so intensity is zero. Then another constructive interference, so the intensity go up. The intensity of the straight through position, okay, straight through, the one in the middle, is the highest because there is less spreading compared to those further out on the screen. You will see that the wave have to spread more. So when the wave spread more, the intensity drops. This is the diagram that is given on page 18. So as mentioned before, we have a double slit and the light source. If the light source you are using is not a laser beam but any other thing else, then you need a third slit, which we call slit S. Some call it a source slit, and some call it a third slit. It is just another slit that you need to put in front of the light source. Reason for this is if you are not using laser beam, the light that is produced will not be coherent when they reaches S1 and S2, although you are using the same light source. So we need to limit the light source from a small part of the light. Then when it come out of S, it will be coherent. Okay, the reason is because of the spreading of the light. So this light source here, right, it will start to spread. Okay, even when there's no slit, it will start to spread. But when it comes to the part whereby there's a slit, remember in the video, later I'll show again, this part, right, will be blocked by, and this part will also be blocked. So it's only this part that will pass through. So we need to limit to this part to ensure that the wave, when it comes to S1 and S2, are coherent. So to repeat, the purpose of the source slit is to ensure that the waves reaching S1 and S2 are coherent. Then you see spreading, and then you have the interference pattern. Okay, at this point, O, I want to highlight O. O is the straight through position. Okay, that meaning if you were to draw a line from the middle of the two slits and join perpendicular to the screen, this is the shortest distance. Okay, so this is called a straight through position. The waves from S1 and S2 will reach O with a path difference of 0. So this will be the central bright range. Why 0 order? Because the path difference is 0. Delta x equals to m lambda. So the n here equals to 0. Then we have the dark region. Followed by that, we have the first order bright fringe correspond to a path difference of 1 lambda. Then we have another dark fringe. And then we have the second order bright fringe or the second order maximum, which correspond to a path difference of 2 lambda. So the same thing happened below. Okay, then this dark region here, it corresponds in the middle here. Dark region, it corresponds to a path difference of half lambda. So this is the first order maximum. Path difference of 1.5 lambda. So that is second order The checkpoint on page 18, on figure 12, that is the diagram given. Identical waves from S1 and S2, each of intensity I0, they interfere at O to produce the central maximum. Deduce the intensity of I0 in terms of I0, the intensity of the resultant wave at O. Okay, so each of the wave from S1 and S2 have intensity I0. What is the resultant wave intensity at O? Then you have to answer, does this violate the law of conservation of energy? From wave lecture, we know that intensity is proportional to amplitude squared. From principle of superposition, we know that the resultant of the wave at O is double. So the amplitude is 2 times that of the individual wave. And if I were to square it, then the intensity now will be 4I0. Does this violate the law of conservation of energy? If I have a wave of intensity I0, another wave of intensity I0, the total intensity should be 2I0. But now, we work out that the intensity is 4I0. So there's a gain in energy. How can I0 plus I0 be equals to 4I0? So does this violate the law of conservation of energy? Answer is no. Why? Because in the dark region, okay, the two waves actually are cancelled, right? So the intensity of I0 and I0 from each of the individual wave is redistributed to the maximum. So the average right across the screen is still a constant, which is 2I0. Since each of the waves have intensity of I0, okay, so the resultant by right should be 2I0, but at the right, at the region where you have constructive interference at O, you find that the intensity is 4I0. Because why? There's an extra 2I0 contributed from the dark region, which is the minimum. Okay, we stop here.